Prediction of cloud server job failures using machine learning-based KNN classification and Lstm modeling methods. Cloud computing is the use of a network of remote servers hosted on the internet to store, manage, and process data rather than a local server or a personal computer. The cloud computing industry has grown to a great extent in recent times, and it is important to make sure that the delivered service does not deviate from the correct intended service. So, to build a reliable cloud service platform, we need to understand and characterize failures. This work aims to understand the reasons for failure and predict failures that might occur in the future. To accomplish this, we use the Google Cluster Workload Trace. Our analysis reveals that an overwhelming number of resources are used by jobs that eventually fail. For prediction, we use long short-term memory network, LSTM, to forecast features on which failure depends. We then predict the termination status using the KNN classification model, which was trained on the existing data. Keywords: cloud computing, predict failures, forecast features, LSTM, KNN classification model. Introduction. Cloud refers to a network or internet. In other words, we can say that clouds are present at a remote location. Cloud can provide services over public and private networks, i.e., WAN, LAN, or VPN. Applications such as email, web conferencing, customer relationship management, CRM, execute on the cloud. Cloud computing refers to manipulating, configuring, and accessing the hardware and software resources remotely. It offers online data storage, infrastructure, and application. Cloud computing offers platform independence, as the software is not required to be installed locally on the PC. Hence, cloud computing is making our business applications mobile and collaborative. The 2020 cloud computing results show that enterprises continue to embrace multi-cloud and hybrid cloud strategies and are already using more than 2 public and 2 private clouds on average. A majority of enterprises expect to increase cloud usage due to COVID-19. The executions of jobs in large-scale data centers are highly complex due to the underlying heterogeneous hardware, intricate dependencies among tasks, diverse job priorities, and sophisticated job scheduling too. Due to the complexity, dynamism, and openness of cloud computing, applications running on them are prone to failures that could affect many customers and could even lead to massive financial loss. To reduce these losses and to make cloud computing more efficient, we need to prevent failures. Many prior studies on large-scale system reliability focus on hardware/software failures and their causes. While these are valuable, they do not provide much insight into failures experienced by end users. Application failures have been analyzed in popular systems such as Hadoop and distributed scientific workflows on Amazon EC2. However, these studies are limited to MapReduce or scientific computations and are difficult to extrapolate to generic clouds such as the Google cluster. In comparison, our work focuses on failure characteristics from the job's perspective and covers broader classes of jobs than MapReduce or scientific computations. 3. Our goal is to identify the reasons for cloud failure. By doing so, we understand the reasons for failures, and we can make suitable changes in the infrastructure. Also, we try to predict cloud failures in the future by using classification and time series models. Literature review. There has been a wide range of research to understand and predict cloud failures. There have been many studies on Google cluster data focusing on failure identification and prediction. Rice et al. 21 present a comprehensive study of the Google cluster traces in recent times. They provide a broad characterization of the workload that focuses on issues such as cluster utilization, job and task properties affecting the scheduler, resource request versus actual usage, and the challenges in task scheduling. Their study identifies 2 important characteristics that may warrant new scheduler design. First, they observe some underutilization of resources, i.e., significant mismatch between resource requests and actual resource usage. Second, they notice substantial delays in the scheduling of some requests that have constraints. Resource utilization and task implementation vary widely. This was studied by Rice et al. 22. Failure analysis of cloud centers was also done by many researchers such as Ford et al. 23 studied the impact of correlated failures on availability of distributed storage systems for Google clusters. Disk failures lead to loss in data, and the major reason for the unavailability in the Google Cloud Storage system is transitory node failures. Analysis of physical machines and virtual machines highlighted their differences and similarities. Burke et al. 24 found that VMS have lower failure rates than PMS, and show a surprising trend that, in contrast to PMS, increasing the computation intensity by VM unit does not increase failure rate. Works which have characterized workload patterns by finding correlations between resource measures and failure are Fadi et al. 18, which analyzes workload traces from the Grid Workload Archive Project 25. They discover correlations between job failures and performance metrics such as memory usage, CPU utilization, queue utilization, exit hour, and migration of jobs, etc. Failure prediction is an important field of research as it will prevent major losses and will help to improve the system. There have been many methods and models which have been used to achieve this task. The authors in 26 have made a good attempt to analyze the failure data of a large-scale production cloud environment consisting of over 12,500 servers, which includes a study of failure and repair times and characteristics for both cloud workloads and servers. Pedocrat et al. 27 proposed a hierarchical online failure prediction approach called HORA. HORA employed a combination of a failure propagation model and software system failure prediction techniques based on Bayesian networks. Zhang et al. 28 designed and implemented a new tool based on random forest, RF, called Prefix, for accurately predicting whether there will be a switch failure in the near future. However, machine learning approaches such as SVM have the same shortcomings just like statistical approaches, so they cannot handle the sequence data well in cloud data centers. Dataset description and preparation. The dataset we are using is the Google Borg dataset. A Google cluster is a set of machines packed into physical enclosures, racks, and connected by a high-bandwidth cluster network. Machines that share a common cluster management system form a cell. A single usage trace describes several days of the workload on a single Borg cell. We have been given data for 8 cells. For each cell we have 5 tables named Machine Events Table, Machine Attributes Table, Collection Events Table, Instance Events Table, and Instance Usage Table. For describing the dataset, we have used Google Cluster Usage Traces v3.11. We now describe each table. Machine Events Table has a 1. Time column, which has a timestamp in microseconds, 2. Machine ID column which is identifier for a machine, 3. Type column which takes 3 values add, remove, and update, which means a machine becoming available to the cluster, a machine removed from cluster, and a machine has its resources changed is available to the cluster respectively. 4. Switch ID column, which is an identifier for the network switch that the machine is connected to. 5. Capacity column, which shows the resources supplied to programs that run on the machine. 6. Platform ID column, showing the version of the chipset of the machine, and 7. Missing data reason column. Machine Attributes Table has the following fields: 1. Time, 2. Machine ID, 3. Name, it tells the attribute name. 4. Value, machine attribute value. 5. Deleted, it takes a Boolean value to indicate whether an attribute has been deleted or not. Collection Events Table has the following fields: 1. Time, 2. Type, description of this column can be understood seeing Fig 1. 3. Collection ID, it is a representation of a collection. 4. Scheduling class, it takes 1, 2, 3 values, where 1 denotes the least latency sensitive task and 3 denotes the highest latency sensitive task. 5. Missing type, it shows the type of missing data. 6. Collection type, this shows the type of collection, which takes two values 0 if the collection describes a job or 1 if the collection describes an alloc set. 7. Priority, a high value of this column means that the priority of the collection is high. 8. Alloc collection ID, identifier of the alloc set that hosts the job. 9. User, name of the user, it is obfuscated. 10. Collection name. 11. Collection logical name, collection name that reflect its purpose. 12. Parent collection ID, it is an identifier of the parent collection. It takes a value of 0 if it has no parent collection. 13. Start after collection IDs, 0 or more unique identifiers of any collections that must finish before this one can start. 14. Max per machine, the number of instances which are preferred to be placed on a machine. 15. Max per switch, the number of instances that are preferred to be placed on machines that have the same network switch. 16. Vertical scaling, if enabled, the system determines how much CPU and RAM to request. 17. Scheduler, the scheduler that was tasked with placing the thing. Values are: scheduler default, the default job scheduler. Scheduler batch, a secondary, batch, scheduler. Data preparation. We focused on two tables which were the instance events table and instance usage table. We merged the instance events table and instance usage table for 100 machines. The primary keys used were machine ID, collection ID, and instance index. After merging the two tables based on these primary keys, we then use the time column in the instance event table and the start time and end time column in the instance usage table to take only those rows in which the time in the instance events table lies in between start time and end time of the instance usage table. We see that one of the reasons for failure is when the value of maximum memory is more than the value of assigned memory as seen from Fig 2. When further investigated, we see that out of 88,794 points which have failed, there are 2 points for which average memory is more than assigned memory, and there are 88,792 points for which average memory is less than assigned memory. For 36,417 points which have failed, there are 4,976 points for which average memory is more than assigned memory, and there are 31,441 points for which average memory is less than assigned memory. If assigned memory is less than average memory, it will surely fail, but when it is higher, it may fail due to other reasons. When the average CPU consumption surpasses the maximum memory, failure will occur. When the CPU consumption is less than the maximum memory, failure may happen due to other reasons. See relation of percentage average with failure. We see that the ratio of frequency of failure points to non-failure points increases with increase in percentage average value, which is the ratio of average memory and assigned memory. So, by this observation we can say that the probability that a point fails increases when the assigned memory/average memory value increases. 3. Modeling and results. Model overview. After pre-processing and merging the instance usage and instance events table, we apply the KNN classification model. The failure column formed acts as our target variable. The values of the predictor variables are forecasted using the Lstm model. Now the trained classification model is used to predict failure on forecasted predictor variables. A KNN classification. B. Long short-term memory. The long short-term memory, LSTM, model was proposed by Hochreiter et al. 10. It is a type of recurrent neural network which can have long-term dependencies. The term long short-term memory comes from the following intuition. The LSTM model introduces an intermediate type of storage called memory cell. Unlike the standard RNN with a hidden layer, in LSTM, each ordinary node in the hidden layer is replaced by a memory cell. Each memory cell is a composite unit built from simpler nodes that are connected through some multiplicative nodes. A standard memory cell of a LSTM consists of the following elements: 8. Input node, denoted as GC, takes activation from the input data point xt, at the current time step, and from the hidden layer at the previous time step h, t1. Usually, the summed weighted input is run through a TAN activation. An LSTM memory cell with a forget gate. 8 input gate, denoted as IC, takes activation from the current input data point xt, as well as from the previous hidden layer data. A gate is so called because its value is used to multiply the value of another node. It is a gate in the sense that if its value is 0, then flow from the other node is cut off. If the value of the gate is 1, all flows pass through. The value of the input gate IC multiplies the value of the input node GC. Internal state. The internal state SC is the central part of an LSTM memory cell that has a self-connected recurrent edge with fixed unit weight. This edge spans adjacent time steps with constant weight. Therefore, error can flow across time steps without vanishing or exploding. This edge is often called the constant error carousel. Forget gate. These gates provide a method of learning to forget. Output gate. The output gate is denoted as OC, which is multiplied by the internal state SC to produce the final value VC of a memory cell. Data preparation for LSTM. LSTM is a recurrent neural network. The input to every LSTM layer must be three-dimensional. The three dimensions of this input are samples. One sequence is one sample. A batch is comprised of one or more samples. Time steps. One time step is one point of observation in the sample. Features. One feature is one observation at a time step. For conclusion. With the increasing cloud usage, it becomes important to understand when faults might occur and try to prevent them from happening. The data available about such workloads and traces is less. I have worked on the Google Borg dataset and tried to understand that why failures occur and how we could prevent them from happening. By plotting some graphs and making some tables, we got some insights about the data. We first built a hypothesis that when the average memory consumed surpasses the assigned memory, failure occurs. We proved this by plotting the graphs and saw that for events which finish successfully, at no time the average memory would surpass the assigned memory, but for failure events this is not true. For events which fail but do not have their average memory surpassing the assigned memory might fail due to other reasons. We also found some strongly correlated columns and dropped some of them. We then presented a classification model, KNN, which was able to correctly identify 9,085 points out of 9176 failure points. The model also correctly identified other events like submit, queue, etc. For predicting events which may fail in the future, we used long short-term memory model, which predicted the input features to the classification model like the average memory consumption, assigned memory consumption, etc. Then the trained classification model was to be used to predict whether the forecasted input features would fail or not. We achieved a good overall accuracy of 94% with a recall of 99% for the classification model and accuracy of around 75% for the LSTM model for the attributes of average memory consumption, assigned memory consumption. The two models, when connected as a ML pipeline, would help in predicting the task/job failure before time. That will help the respective team to take proactive actions to prevent the same. This work would help in improving the cloud server infrastructure, monitoring, and management, and we hope that we contribute in improving it by our work.